for the project that we've been doing in the VIP for fall 2023, reinforcement learning for vision-based manipulation with Handy. This is a project that's been done by me, Anthony, Ritesh, and Abdul Latif, and we're all OMSCS students at Georgia Tech. So the outline of our presentation is going to be basically our goals for the semester, talking a little bit about reinforcement learning, the Handy environment, Gymnasium Interface, and some of the deliverables and future work that we're aiming to do for this project. So really quick, our goals for this project are outlined in this document. This boils down to basically 3 major goals. The first is to play around with OpenAI's Gym, or the Gymnasium Interface, for reinforcement learning, to build a reinforcement learning for a manipulator environment. And then we want to build a custom environment that does a very particular task, which is manipulation with a camera that's mounted on the wrist of the manipulator, so that we don't have to do camera calibration and we can do a specific reach task in a simulation. From that simulation, we want to build a custom environment that aligns with the Gymnasium interface. And finally, we want to train an agent in that interface. So at a high level, that's kind of our goal. It's to explore reinforcement learning, to build a custom environment with the robot that's in the lab, and to train a model that is able to interact with that simulated environment. So to talk about reinforcement learning, I'll hand things over to Ritesh.
Thanks, Anthony. Hi, this is Ritesh here. I'll go over the reinforcement learning piece of the project. So talking about the big picture, reinforcement learning essentially is where we have an agent and we have a fixed environment, and agent takes some action on the environment. Environment is supposed to give it back a reward and the next state, and the agent learns from it and tries to basically maximize its reward from this environment. And it takes in the beginning, it takes random actions, and eventually it learns and optimizes its policy and comes up with a good policy to be used for later on. Next slide, please. The training of the agent usually happens in a discrete or a continuous space. In a discrete space, you have to build up a table. In continuous space, where we have a large continuous area, building up a table is kind of becomes almost impossible. The size becomes too huge to be able to handle. Just for a little example, a chess game, if you were to put it in a table with a branching factor of 35, there will be 10⁴ kids. So that probably is not going to be able to store somewhere. So there are some algorithms that have been developed by researchers for this. And some of the most popular ones are PPO, DDPG, DQN, and TD3. They have their own full forms. One of the easier ones to remember is the DQN, which is the Deep Q Learning Network. And so these algorithms help the agent in optimizing its policy sooner and in a continuous space. And we'll be using PPO for our project because that seemed to be the most popular one, and for robotics application. PPO stands for Proximal Policy Optimization. It is one of the popular algorithms, and it has some unique features when compared to other algorithms. The algorithms are kind of broken down into 2 domains. One is where you have policy gradient algorithms, which PPO uses, and other type of algorithms are called actor-critic algorithms, where you have the DDPG and the other ones that I spoke about. In policy gradient algorithm, we directly work on the policy itself, versus in actor-critic, there are 2 pieces to it. One updates the policy and one tries to make it fixed. So we're not going to discuss about that much in here. Policy gradient algorithms are very suitable for stochastic environments which is what we would usually deal in robotics, where when we take an action, it is not always 100% that the action will be taken. Sometimes it may happen, it may not happen because of the misbehaviors of the robot. And this PPO algorithm is suitable for continuous or discrete space. So it is versatile in that manner. And it uses special mechanisms. If you read the literature online, there are some special other mechanisms that the algorithm uses to update its policies. Next slide, please. So here is a trained agent. So we used the fetch reach version 2 environment from the Gymnasium Robotics API, which uses a Mujoko physics environment behind the scene. And as you can see in this one, the manipulator is always able to reach to the red dot, which is its target, in this scenario. This agent was trained on 1 million timestamps, and we use the stable baselines 3 library, which has implementation of a bunch of these algorithms, and we use the PPO algorithms from that library to train the agent, and it was consistently able to kind of get to the target every time within a few timestamps. You can go to the next slide. And yeah, that's it from the reinforcement learning side. I'll hand it over to Anthony.
Or to Abdul Latif.
To Abdul, sorry. To Abdul, thank you.
Hello, this is Abdul Latif, and I will be speaking about the handy environment part of the project. Next slide, please. So as of today, we have the handy environment loaded in Gazebo and in Arviz, where we can visualize its state space. And all of that today is packaged inside of Docker containers, so it can be easily built and deployed. And can you go to the next slide? One of my main tasks throughout the semester is to develop a ROS node that will take an image that is captured by the camera that we have in the scene and convert and extract the image embeddings as a vector out of that image. The image to vec node depends on a concept that is called transfer learning, in which we take the learned knowledge from a pre-trained model, such as the ResNet 18 that we're using, and use that to help with the new learning tasks. In our case, that would be the agent. After implementing that, I was able to take the image as input and broadcast an embeddings out of the image received. Next slide. Furthermore, to test which layer would be better in terms of extracting image embeddings from the neural network, I was experimenting with cosine similarity. So I took 2 images of a pup and a cat, and when we're running that between the cat and the pup, it resulted in approximately 2.48. And between the 2 puppies, it resulted in a higher similarity. Now, this was run on images, but while doing unit testing for that neural network, it will be done on 2 image embedding vectors. And this will be added as a unit test to the image to vec node to find the best layer to extract the image embeddings. Furthermore, what we're trying to achieve here is to move the camera and attach it to the end effector or the grepper. And it will be something that looks similar to what you're seeing here in the image. If you go to the next slide, you will be able to see the actual work done on the RDF models for the handy environment, where you can see the camera is attached on the grepper. Currently, we have the RealSense D435 camera URDF model and the handy as 2 separate models. What I was doing is attaching these models together, and there was some complexity while dealing with 2 separate models and trying to integrate them together. Yep, and I will be handing over to Anthony.
So I'll talk about the last piece of the project, which is this Gymnasium Interface. This really ties together the idea of reinforcement learning with our custom environment for doing vision-based manipulation. So in order to provide an interface between the reinforcement learning algorithms and the Gazebo simulation environment, we have to have an API that we can use to train those models in a consistent way. So one of the things that we did was build a REST API for the state controller. And so what the state controller does is it will interact with the ROS environment. So it will publish and subscribe to various ROS topics and ROS services in order to build a consistent blob that we can use to communicate between the Gymnasium API and the actual simulation. Here we show a JSON response from a ROS node that is able to interact with the simulation. And this is what we would use in front of the Gymnasium API that's implemented in Python. At a high level, what this looks like is we'll have some sort of REST API that can talk to various environments. So each of these might be a separate Docker compose environment that has its own position estimate, its own look at the environment, and a state controller that provides that API between the environment and the actual reinforcement learning algorithm. So this very modular approach is supported by ROS, and so we want to take advantage of that and to implement that. Unfortunately, this is something that is to be left for next semester, but we do have some validation that this approach is going to be effective. So the deliverables for this semester involve all three of those components: the reinforcement learning stuff, the handy environment stuff, and the Gymnasium API stuff. So as you saw the demo of the PPO algorithm on a manipulation task. We also have a GitHub repository under Autobots Visman reinforcement learning that has all the code that we've written for this semester, which includes both the reinforcement learning stuff as well as the handy environment and all the ROS nodes that we've developed over the course of the fall semester. Future work involves things like completing the integration of the camera on the handy end effector, the integration of the Gymnasium API, learning a policy on the actual simulated robot, doing some deployment of the training, deployment of the learn policy, and just validating that initial hypothesis that we had on doing reinforcement learning with handy in a way that allows us to avoid camera calibration on the actual robot. So this is work that we'll be doing in the spring of 2024 with this team. And if you're interested in joining our group, then reach out to us. We're more than happy to accommodate new people who are interested in working with reinforcement learning and working with vision-based manipulation. So that is all for our presentation. Thank you.